So today I'm going to try very shortly to represent to you the steady state fluorescent quenching method for evaluation of nano-bio interactions. So I'm going to talk to you about something about the meaning and importance of protein corona. Then very shortly, I'm going to present the methods that are used for evaluation of protein corona. And we are going to focus on a steady state fluorescence quenching method that we are using in our lab to investigate nano-bio interactions. Also, I'm going to present very shortly some of our results that we got, and we're going to have some conclusion marks. So first of all, when nanoparticles enter biological system, they become immediately covered with different biomolecules, and this causes the formation of so-called dynamic biomolecular layer, which is also known as protein corona. This is important because this protein corona actually changes the physical chemical properties of nanoparticles, and therefore changes their fate in biological systems, their pharmacokinetics and pharmacodynamics. But also it can change proteins, so it can cause the irreversible change in their structure, which can lead to the loss of their functionality. It is important that composition of this protein corona is actually changing based on some pathological conditions, for example, in cancer. And therefore, it is important to investigate the mechanism of formation of this protein corona. So methods that are used for evaluation can be basically categorized in three groups. First groups are the methods that are used for identifying the changes in physical chemical properties of nanoparticles, like dynamic and electrophoretic light scattering, transmission electron microscopy, that are used for determining the changes in shape, size distribution, or zeta potential, whereas atomic force microscopy is used for determining the surface changes in the surface structure. Second categories are methods that are used for determining the changes in structure of the protein, like circular dichroism and NMR. But also these interactions can be evaluated using fluorescence spectroscopy and surface plasmon resonance method. And at the end, third category are the methods who are used for determining the composition of protein corona, like electrophoresis and mass spectrometry. So today we're going to focus on fluorescence. What actually fluorescent theoretical background is that when molecule is excitated from the ground to excited state, it absorbs the energy, which it loses in excited state through vibrational relaxation, and it goes back in the ground state, emitting the photon of light, which is lower energy but higher wavelength. It is important that in the proteins, the fluorescence is actually coming from aromatic amino acids, and the highest contribution to this fluorescence has tryptophan. That's why when we are evaluating interactions, we are using the wavelength of excitation at 280 nanometers. And we are actually monitoring emission spectra from 300 to 450 nanometers. So the maximum intensity in fluorescence, the wavelength depends on type of the protein. So it's not the same for every protein, of course. So first, when you're starting the experiment, we are measuring the intensity of fluorescence of protein alone, which is this black spectra. And after that, we are doing actually titration. So we are increasing the nanoparticles concentration, and this intensity is quenched. So these nanoparticles are causing the quenching in the fluorescence. What is important is that you can have two types of quenching. First one is static quenching, which is actually happening due to formation of non-fluorescent complex on the ground state between nanoparticles and proteins. And the second type is dynamic quenching, in which one molecule is transferring energy to another one in excited state. So when you have all these parameters, the concentration of nanoparticles you are using and maximum fluorescence intensities, you are putting it in this Stern-Volmer equation, where F0 actually represents the maximum intensity of fluorescence of protein, and F is fluorescence after adding a certain amount of nanoparticles. And you're making this kind of plot where you actually want to determine the slope of this linear curve because it represents the Stern-Volmer constant. From this constant is actually, it's allowing you to calculate the quenching rate constant using specific tau value. Tau is actually the time of fluorescence of tryptophan in the absence of a quencher. So for us, because the tryptophan contributes to the fluorescence of the protein the most, you're using its tau value, which is 5 nanoseconds. And you can calculate this quenching rate constant. If it's above 2.10 on a power of 10, you actually have static quenching, and this has been described in the literature. After that, you use this logarithmic plot, and from this plot, from this linear curve, you're determining the intercept and slope. Slope is actually Hill's coefficient, and of course, intercept is a logarithmic value of constant of binding, and you can actually get the constant of binding between nanoparticles and proteins. Hill's coefficient is actually telling you what kind of binding do you have. Do you have cooperative or anti-cooperative binding? Cooperative actually means that one attachment of one molecule on the surface of nanoparticle is actually allowing the other molecule to attach more easy. What is the problem with this method? The problem is actually this interference that it's called inner filter effect. So as we all know, actually nanoparticles are absorbing the energy. And because of this energy absorption, they can cause this effect. So if nanoparticles are absorbing the excitation light, then you actually have primary inner filter effect. And if they are absorbing the emitted light, you have secondary inner filter effect. How can you actually determine do you have it or not? It's very easy. So you have nanoparticles actually have some kind of fluorescence, but this fluorescence is not that high. So intensity is up to, let's say, 10 units. And as long as you have a linear relationship between fluorescence and concentration of nanoparticles, you're actually in the range where you don't have this effect. At some point, the absorption inside of the cuvette becomes high, that this fluorescence will not be in the linear relationship with concentration. How you can avoid it? Well, first of all, you can work in a very small concentration range where absorption on the excitation and emission wavelength is below 0.1. You can reduce the path length of the light by using smaller volumes or smaller cuvette with smaller path length. Or you can change the excitation wavelength on some other excitation wavelength where nanoparticles are not absorbing that much. If it's not possible to avoid it, then you can use this correction formula. You only need the absorption of nanoparticles on excitation and emission wavelength. So what is actually our research? So first of all, our aim was to investigate the influence of glycosylation and different physical chemical properties of nanoparticles on nano-bio interactions and formation of protein corona. So why glycosylation? Different types of glycan pattern are found in some pathological conditions. So this glycan profile is actually changing depending on pathological state, for example, in cancer, but also like in diabetes or some other conditions. So this fundamental research will improve the development of later cancer diagnostics. So we used model protein transferrin because transferrin glycan profile has already been used in clinic for some conditions, for example, to determine chronic alcoholism or congenital disorder of glycosylation. So it made sense to use him. And of course, bovine serum albumin was used because most of the research has been done on it. So that it will make our results it made our results more easily to compare with already published ones. We used different types, different sizes of citrate gold nanoparticles. We used differently coated silver and gold nanoparticles, and also different shapes of gold nanoparticles in order to determine the influence of size, the influence of coating, and the influence of shape. So what were our results? So as you can see here, proteins were acting, the constant of binding between proteins and nanoparticles was depending on a type of protein, because with BSA, the constant of bindings were increasing with size of nanoparticles. These are citrate small, medium, and large. Whereas with transferrin, we had opposite trend. So with increase of size, the binding was decreasing. Also, when we are noticing the influence of shape, so this is spherical ones, gold nanoparticles, rods, and prismas that were all same coated with PEG and in the same size. So rods actually had the lowest binding with all three types of proteins, which was different compared to spherical ones and prismas. Also, when we are looking at the influence of coating, we can see that we obtain different results. For example, PEG, gold, and silver nanoparticles had lowest constant of binding for BSA and non-glycosylated transferrin, which made sense because PEG is usually used as a biocompatibility agent. But this was not noticed for glycosylated transferrin, which may be due to hydrophilicity of PEG, because glycans on the surface are actually making the protein more hydrophilic, and therefore maybe the environment was more better for the attachment of PEG coated nanoparticles. On the other hand, where we are watching the citrate, gold or silver nanoparticles, the attachment, the binding was lowest for glycosylated transferrin, which again may be due to glycans, because glycans are actually containing sialic acid, and this sialic acid is actually negatively charged, and citrate has a very negative charge, and therefore this may be due to electrostatic repulsion. This is results we obtained from circular dichroism. It will be very short. I just wanted to show that we here also notice the influence of shape. So for the large citrate spherical gold nanoparticles, they caused the biggest changes in structure for both glycosylated and non-glycosylated transferrin. And here also the influence of coating was noticed, but also the difference between glycosylated and non-glycosylated transferrin. For example, glycosylated transferrin did not show any structural difference with attachment to PEG nanoparticles, whereas non-glycosylated did. And also here we can see that, for example, rods nanoparticles cause the biggest influence on structural changes of both transferrins, which may be due to their morphology, because they are cylindric. and this curved surface might cause the bigger changes in conformation when compared to, for example, prismas, which are actually more planar. Our future research would be to see the competitivity in binding between all three proteins. We're going to incubate all three proteins with differently shaped nanoparticles individually. And after incubation, we're going to deattach nanoparticles and analyze composition of protein corona on using SDS page and mass spectrometry. What we actually want to see is this Raman effect. So we want to see whether these affinities that we gain can be somehow connected to the composition of protein corona, because according to Raman effect, when the bigger affinity of the protein for nanoparticle is, it will attach more in. He will have more higher concentration in corona. So the conclusion would be that this was the first study which evaluated the influence of glycosylation status on proteins on the formation of biomolecular corona. Nano-bio interactions are highly dependent on multiple factors like physical chemical properties, but also the structure of the protein and its glycosylation. So of course, glycosylation have a significant impact on biomolecular corona formation, and therefore it can influence biological fate of nanoparticles in the body. And at the end, I would like to thank Cost Action Nanoto Clinic for giving me and allowing me a short-term scientific mission grant, which I used to go to the Institute of Material Science of Aragon in Spain, Zaragoza, where I actually had very great opportunity to learn under Professor Martinez de la Fuente and Dr. Rafael Martin Rapun. And also I would like to thank my supervisor, Dr. Ivana Vinkovic-Vercek, for encouraging me to apply for this grant and for being a great support during these 3 years of PhD. Thank you.